Hello? It is time. All right. Balancing. I need a more involved way of selecting just like choosing what to do. I'll just reset that. I don't think I'm running. Yeah, I mean, I'm just doing my own test now. Well, exactly. Yes. Okay. I wanted to look at what I had before, but I think I've kind of lost a lot of that. There was a thing that I saw. Do I have the... No, why would I have the output? Because I... Okay. Run this. Stop it, because it happens right at the start, I think. Yeah. So I'm looking at something that happens here. These values are kind of okay. And they hit this point. And then these flip to negative and this goes over 1. Right? But it's still continuous so far. It's still continuous until this point. Essentially, the sign of everything flips. And maybe there's a little bit of a change between these two because the first number stays sort of close. Second number stays sort of close. This number changes by like 2 units of absolute value. But there's like a discontinuity here that happens. Well, first of all, it goes negative, which is bad. And then in a way, this middle one is making up for the fact that the other two are negative. Like I said, it is still continuous at this point. Values are changing slowly over time. And yeah, this one goes from like -1 to -3 in a single, like a 60th of a second. This one, I guess, also goes from 3 or like 4 to 11 in a 60th of a second. This goes from 2 to 7. So there's like almost like the shape of like a tangent graph, where it gets close to an asymptote, and then it accelerates up to a really extreme value, and then it pops over to the other side at basically the exact negative value, and then it is a little bit more stable after that. Still a negative value here, though. And everything becomes positive for a bit. Did I let it run long enough? Yeah, these are all like very, very stable configurations, I think. Although I'd say this maybe doesn't make too much sense because I believe how does it rotate again? At what point does it? Yeah, so this is alright, so this is this one on its own side, and then these two are on that side. And it's pretty nice and it's sort of like in a stable place, but then about around here it's gonna get really, really bad, yeah. So this goes over 1 and this becomes negative. Well, this one was already negative. And then I just saw it go from like 2 to -12, and this one went from -4 to 38. 3 to -25. So yeah, there's like some kind of crazy... Oh, a flip just happened. From 1 to -1, 1 to -1. And I think it's going to be another flip. Yep. From 8 to negative, or like 9 to -11, -5 to 9, -2 to 4. So it's like when these points cross over each other, basically. When like a point becomes linear with another one in the direction of gravity, I think. So that one didn't happen. It happened earlier than it should have, I think. But yeah, 93, 47, 134, or 139. Like, I'm assuming exactly on those points, it probably can't compute a solution. Anyway, yeah, there's definitely some kind of like asymptotic. There's a point where my method can't produce a solution because the values explode to infinity. In all directions. So I need a more involved way. I think my idea, and there's like a general idea here. I think the general idea is I see what each point is doing. Generally, you probably want to pair points up. So you want one point to balance against another point or a set of other points. In one dimension, this is pretty simple. You have to have a positive rotation or a negative rotation, or you have a zero rotation. In that case, that point can do whatever it wants. That point can be like an equalizing point, where you can give it a higher value or a lower value so that the ones that are applying rotation are doing a little bit less work, right? Because I think generally I want to minimize. I kind of want to do two things. I think I want to prioritize sharing the work between all the legs as much as possible. And any time where a leg has to have more work done to it, I would prefer a leg that is doing less rotation. I'll prefer a leg that's closer to 0. In the case of 3 legs. And then I kind of need, I mean, this... Right. So if I have a leg, and I mean, I think I probably need to jump up to 3D, really. I think 2D is too simple. I'm gonna struggle. I don't think there's gonna be a natural expansion up to 3 dimensions because there's too many shortcuts that I can take in one. It's sort of the case where if I was good enough, I could start in 2D with 1 dimension of freedom and build a system that's robust enough to handle up to 3 dimensions. But there's like complexity that I think maybe just jumping to 3 dimensions is probably going to be better for me, because otherwise in 2 dimensions I might just take shortcuts that just simply do not work. Yeah, so probably do that. But I like this. I like the layout that I have here. I basically have a body that I start spinning, and then I have a set of points around it that are essentially anti-gravity points, just wherever I want them to be. They don't alter the rotation of the body. They should never alter the rotation of the body. So let's go for that. A 3D scene. Balance body 3. Start with the camera. It's probably too high. I'll go with a capsule shape. Like a capsule shape's probably gonna be. I'd actually like a shape that's not really uniform. I guess I can do convex, and I can just kind of throw points in there. Yeah. It's a convex, but I can't really make. Is there? I'm assuming concave is not. Yeah, you can't even plug anything in there. I'm gonna make like a specific shape that I'm going for here. Mm. This is kind of like a weird, crazy shape. Sure, they just have a convex. Okay, maybe not. Is it possible to make this shape out of meshes? Maybe, I don't know. Alright, I'll just make a bunch of boxes. What? I literally have it set so that it's supposed to... Oh, it's the other way around. Of course. Um... I'm trying not to make it like a regular shape. I just got a weird shape now. Cool. Strange shape. For like a... Hopefully just a really weird mass distribution and... whatever, right? What were these? I called them like force points, but might have been unnecessary. There's also kind of an issue with 3 dimensions where it's actually really hard to get the full range of orientations that an object can have, because there are many, many orientations of an object in 3D space. Okay. All right, roughly triangle shape. I don't know if I really need that, but I'm gonna do it anyway. They really only need to be node 3D. System integrator. Solver. That's all I do. Oh, and I'll make this the scene. And I should just see it fall. Cool. I guess I need to add an environment to this. Cool. Cool. Okay. All right. Is there a way to like initialize it with a size and the value? and a single call. No, okay. I think it's like global position minus state transform origin. Right. Cool. So it is now not falling, but it is rotating a lot. Zoom out a little bit. Now I do want to draw the points, so I guess I can just use debug draw in this case. But I guess I need like that array of things, so um cool. All right. And then I also want to draw their vectors. think I was missing that. I think this is a little bit too powerful. Right. Multiply by step. But it's also times mass. So yeah. Cool. Okay. Um Can't see him. Okay. Really? Well, actually, it should be. Uh, hmm. Hmm. I think it should be this. Essentially, what I'd like to see is the vector be 2 if it's 1, and then 0 if it's 0. No. Or more or less, the largest value becomes the full length vector. So if they're all equal, then they all have a high, they'll have like the full size vector. If one of them is half and the other two are a quarter, then what you would see is the half one is the full length and the 2/4 ones are a half length. So it'd just be the value over the max force. So I guess this could be the value over the max force. But I gotta do it the other way around. So it would be the max force is gonna be the debug vec divided by forces. So this would be like 0.5, and this would be 0.5. This would be 0.5, and this would be, or no, wait. Because I can't do forces over the vector, I guess I can do max. Yeah, I guess I can do that. Yeah. Um, just say that. That'll be forces times debug vec over the max force. So it'll be 2 if it's the largest value. Okay, maybe it was a little bit too large. I'll just go to 1 meter. Okay. So I'm just gonna do this where I'll just do that. So yeah, now if I were to look at the lengths of these, then these two are about half the length of this one, and that one's like the full 1 length. Right, okay. I need a better color though. Guess like gold. Maybe this color. No, that one's actually just difficult to see. I mean, no. I mean, only red really contrasts with blue. I'll make these bright, and then I'll make these like a very dark green. All right. What about purple? Bright purple. It's kind of hard to see. Alright, I think gold is probably gonna be it. Yeah, okay. Alright. Now, to write this method, calculate forces. It should also receive state. And so I go through the force points. I get their local position, and then like over here, I did the math to determine how much a rotation of its current force would do. Why does it not even like this line? Oh. Can I assign a value type vector 3 to variable point with vector 2? Ah, of course. I not declared. Right. So it's not, I don't think this is the same. I think it's a little bit different for the body, that body, so. I think it's add impulse. I think it's motion properties. No. Oh man, so where is it? Inline, add impulse. Set angular velocity to get angular velocity plus. Multiply world space inverse inertia by vector. That looks like the exact same thing, actually. Multiply world space inverse inertia by vector. Takes the body's current rotation, which is, says quaternion argument, but that's just the basis. Don't care about that first part. Multiply vector by inverse inertia. I think I already did this before. I think I literally do this in the Yeah, I already do this in the simulation, or the virtual stuff, which is just taking, yeah, I've already got it. I actually already know that. That one is confusing. I don't know how I figured that one out, honestly. By reading that, because I just read that and I don't know how I do that. It's in here though. I've got it right here. At the end. So the basis is basis rotated. And never mind. Never mind. Rotation, inertia rotation, inertia diagonal. Huh. They do cross. Angular velocity add. So it's just this term. So it's this term, which is just multiply world space inertia by vector. And INV is position minus M position cross impulse. You know what? Let's find Godot physics. I'm sure it's the exact same thing. It's just not as crazy looking of a thing that's hard to figure out what any of the values are. I just have to go find Godot physics 3D. Body apply impulse is body apply impulse. Okay, yeah. Inverse inertia times position minus center of mass cross impulse. So I gather other values, and then I will do... Right, I'll just see this. First run. Right. So because of... Okay. Because of the current orientation of the body, it shouldn't apply yaw. I think it should actually never apply yaw. If I keep stepping through this, I won't see it ever apply yaw. That's my theory. Maybe I... Continue. Why don't I see anything change over there? Why did that have to run like several times? Huh? Why did that run like several times? Yeah, but I've never seen it apply in a yaw. Let me take the breakpoint out. Yep. Never in yaw, so that's cool. However, I don't know if I should make that assumption. Technically, the body will build up an angular rotation that's like this. But as far as like local space on the body is concerned, those points are never applying yaw to it. Global space of the body is concerned, they're never applying yaw to it. They're always pushing up. It's only doing pitch and roll. Also, I think I'm going to go and fix that pop-out thing and just make the size smaller. It was like 960 something. 960, 540. Yeah. Right, cool. Okay. Hi, Elio. Playing Pragmata, my impression so far, Capcom's trademark one-dimensional main character protecting Baby Yoda from Skynet. Okay. So you're saying it's uninspired? Just want to look at this one line. How would I balance that? Child is giving me the creeps. Well, from my memory, it is like not a child. It's just someone decided to put a computer into a baby. So yeah, that would be a little creepy, I think. So looking at this, the only way to really balance it is to balance that left one against the two right one. The two rights. Somehow. So if I were to try to pair these up, Alright, I want to pull something up. Because this was something I was trying to like visualize and trying to get I think I need to finish watching this video. Because I don't know if I can really use it, but it looked like I would. There's something really cool about this. It gets cool when he starts over here with the matrices.
First, he writes the equations corresponding to the two pictures. He uses...
I think R was the one who linked me something about the origin of the child, if I remember correctly. Planning for a pet, but they thought it was too generic, so use a child instead. Uh-oh. Wait a second. Wait a second. So you're going to be a guy with a gun and an animal following you, fighting robots. And they didn't want to do that. Interesting.
Is D for dog and W for wall. Wall plus dog is 300 and wall minus dog is...
I got like really excited at some point during this because they showed a way to find a solution from a matrix layout. And I was like, wait a second. If I could make my problem look like that problem, I could find a really good solution. But I think I can't really make it look like that.
200. Two linear equations at a time is called a system of linear equations.
He lost when I saw the printed tweets. He's gonna make great videos, honestly.
He goes on to write this.
Well, it's more that he shows really kind of obscure stuff about math that I think is like, wow, that's an awesome tool to have. I think I brought this up very recently too, because I was saying balance one leg against the other two legs, which just means like pick some value, stick to that one, and then make the other two work with that value. If you take a stick, you make one cut, you can force the next cut to give you a triangle every time. Was kind of an idea.
Smaller triangle.
I think it's even at the point that I was trying to show, but
system using matrices, which, as you can tell,
I want
are
to finish watching
just rectangular arrays.
I don't know what that was.
This
I don't know
one
why
here is the coefficient matrix, storing the coefficients of the variables. In this system, they don't jump out at us because they're all plus or minus 1, but those are the...
Essentially, I've got something where I have a coefficient and my coefficients are, I mean, this is it, right? These are the coefficients. And then I have some set of variables that I multiply these by. Those are the unknowns. And then that equals a set of some impulses that sum to 0.
Coefficients.
But this one's different because there's like multiple equations.
One,
So I don't know.
one, one.
I don't know if I
negative
can
one.
make it. I
Hence,
don't know if I
we
can
get
make my problem
this
look like that
coefficient
problem.
matrix. This one-column matrix is what we might call the variable vector, storing the unknowns dog and wall. Over here is the constant vector with 300 and 200. Now, these two matrices are being multiplied, and the way that works is the rows get matched up with the columns. So this first row would get matched up with the column.
Okay, I think we all know how to
produce
multiply matrices
W.
and vectors.
The Gabriel rule and Stigler, who is using Kramer's rule, named after Gabriel Kramer, who published it in 1750. However, as we would expect by Stigler's law, a long unpublished manuscript from 1729 shows that the brilliant Colin Maclaurin had made use of Kramer's rule and maybe even taught it to his students more than 20 years before Kramer published it. Either way, Kramer's rule works for any number of linear equations. It will certainly work for the two we have here, and it uses something called the determinant. For two equations specifically,
So this is the thing. So these are my unknowns, right? X and Y. My constants would just be the leading things, and then my coefficients would be these. And my constants would be 0, I guess. But it seems like the problem is the size of these matrices get very, very large. I don't know how I can put 3 values in one value. I mean, I can probably split it, perhaps. I mean, I could probably do that. Like, the x coordinate could be the coefficients, and the y coordinate. I would just ignore the y coordinate because I'm not going to add it, but I can do it anyway. And the z coordinate would be the coefficients. And those would be each of my systems of equations, or all my equations. So out of 3 equations. And then each of these would be 0. But I do happen to know that it probably wouldn't work because, at least in this setup, he's going to get there. I'll let it play.
says the solution is this. These might look like matrices, but in fact, the straight bars mean
I'm just gonna play
determinant.
my music.
Mr. Dovasco used the alternative
He plays his own music, but
DET
it's I can
notation,
tell it's like
which
overlapping.
means the exact same thing. Each denominator is the determinant of the coefficient matrix. You can see those are the coefficients of the system. The numerators have almost the same thing,
I've got my balance
except
all
for the
wrong.
first variable, its first column is replaced by the constants. And for the second variable, its second column is replaced by the constants. This might seem a bit haphazard, but indeed, it works. Computing determinants can be a headache, but at least in the case of the 2x2 matrices that we have here, it's straightforward. All we have to do is subtract the diagonal products. So the determinant of this matrix, 300 times -1, minus 200 times 1. That's why we see negative 300 minus 200. The determinant of this matrix, 1 times -1, minus 1 times 1. So, -1, -1. Doing the computation, we see 250, that's the value for wall. And for dog, we do a similar thing and find its height is 50 centimeters. So that's a very cool, simple example of Kramer's rule, which, like I said, works for bigger systems of linear equations too. So with Kramer's rule, we could solve more sophisticated dog and wall problems also. Like, how about a dog-frog wall problem? Well, now that we have 3 unknowns, 2 cute pictures and their corresponding equations will not suffice. For comparison, if we consider the system from the previous problem with just 2 unknowns, the 2 relevant equations are lines, and we can graph them to find the unique.
This was one thing that I wanted to, so this is getting to a point that I was really thinking about, and I was trying to demonstrate myself using this, which is funny because I'm pretty sure he uses a visualization using Desmos 3D calculator. But I was like, I know that there's like some higher dimension surface or something.
Solution.
And there are solutions along all these intersecting points.
But with 3 unknowns, we leave the constricted two-dimensional plane behind and leap with drama and flair into the 3rd dimension. Each equation represents a plane.
That's literally this. It's literally this. It's literally this.
And 2 non.
Sorry, I wasn't really paying attention to the chat. It's always mind-blowing to me when I see cool tech using math from 1800s or Google's new memory optimization thing. The amount of math needed to make a woman and Norma makes me want to change my sexuality. Who is Norma? And yes, there's a lot of math involved.
Unparalleled planes intersect in a line. Hence, infinitely many points. And so, to actually solve such a problem, we need one more picture. So here's a solvable dog-frog-wall problem.
My guess is maybe I set this up and I have my coefficients, and then the 0 function, these zeros in the middle, suddenly change it to be like a 0 division or something. Like maybe this is set. Maybe this can be set up.
We begin by writing the equations. Then we can turn those equations into matrix form. Now, with the system written as a matrix equation, Cramer's rule applies just as before. Here are the values of the 3 unknowns.
Like, is the determinant of a 1, 1, 1 matrix 0?
Again, notice how the denominators have the determinants of the coefficient matrix. The numerator.
Can I even do? I think I can. I think you can hijack basis, because I think it supports determinant. It does have determinant. So I can set up a basis and just use it for determinant. So yeah, let me just see if determinant of a 1, 1, 1 basis is 0. Channel point check. I kind of wish I had channel points. I don't. I just have infinity all the time. I can't even see. Have you ever done determinants before? Yes, I have. What did you do them for? What were they for? Because I have never done it. I'm writing this in the wrong place. Yeah, that's what I thought. In linear algebra. Okay, I meant like an application of their use. It means a matrix is not invertible. This doesn't do anything extra, right? Whoops. Okay, why is determinant used so many places? And it's not there. Zero times, so that's a diagonal, times 1 times 2 minus, and then I don't know which one those are. Inverse. The inverse of this basis matrix. Invertible matrix. Okay, so I'm gonna I'm gonna do something. So it's about what it means when the determinant is 0. What does it mean when the determinant is 0? What the hell? Matrix not invertible. Okay. I honestly thought that was just like negative values for some reason. I just straight up thought, oh, the opposite of a matrix, or the inverse of a matrix is just take the negative sign. So yeah, that idea is already bust because the determinant of this is 0. Which means I would have to be dividing by 0. So I can't do that. I mean, like I said, I guess I could just ignore it because I know I'm not going to get that one. So I could just drop that. All right, so how do I set this up for? I'm just
Are similar, but the first variable has the first column replaced by the constants, then second column replaced, and third column replaced. We saw that to calculate the determinant of a 2x2 matrix, you just need to subtract the products of the diagonals. But what about a 3x3 matrix? These sorts of determinants can be calculated with this snappy formula. 2 matrix, you just need to subtract the products of the diagonals. But what about a 3x3 matrix? These sorts of determinants can be calculated with this.
My question is, how do I build the top, though? How do I build the
a
top?
formula, which isn't as bad as it looks, but it is a nuisance. In the end, using that formula, or secret tricks if you know any, we arrive at these solutions. So yes, substance.
This is why we have GPUs. So what if I have a line with all zeros? Also, the column. Okay. Can't you hear over Overwatch? Okay. So yeah, what if one of these was wait, what? Constants. That's X.
And for this,
Wait, what? The constants with B. Okay, so it's just replace that one's coefficients with the constants. And then you just use the coefficients of the other ones. Okay. So it's like the determinant of all the coefficients, except you replace the one you're looking for with the constants.
second variable, its second column, is replaced by the constants. This might seem a bit haphazard, but indeed it works. Diagonal times one rule. How about a two equation leap? Learn the equation. Kramer's rule applies just as before. Here are the values.
Yeah, what if that's 0? So then I have just a row of zeros and then I guess just all ones. What is this one? Don't be 0. Why is it still 0? I mean, it could be like 1. It could be like 0.5, negative. I don't know. I'm just making up numbers. Hey, Neon Riftborn, thanks for the raid. Hello. That's not 3 numbers. I have no clue if this... I'm just making up numbers. What is that one? Still 0. Right, so I can't have a 0 as any column. Be better off pirating a linear algebra textbook. So if there's a... So I'm not sure about. Column major. In row major. But I make the call. I don't understand. This is what I don't get. Am I giving a column? Or am I giving a row? Is this the top row or is this the first column? I mean, I could write that and then that flips it. Let's just change it. Still 0. Man. Alright, yeah, I mean, that's just a bust then, because I would have to have zeros so that doesn't work.
Of the
Yeah, when I
three
finish watching the video, though.
unknowns. Again, notice how
How-
the denominator
I thought I might be able to use this. I can't, which is sad. I mean, I guess it is the case where in this layout, there is one solution. In my layout, I already know that there's an infinite number of solutions. But there is like an ideal solution. No negative numbers, no zeros. Or I guess avoiding zeros. And make all the force points apply as close as possible to the same amount of force. I feel like I'm trying to use math like it's
have
magic.
the determinants of the coefficient matrix. The numerators are similar, but the first variable has the first column replaced by the constants, then second column replaced, and third column replaced. We saw that to calculate the determinant of a 2x2 matrix, you just need to subtract the products of the diagonals. But what about a 3x3 matrix? These sorts of determinants can be calculated with this snappy formula, which isn't as bad as it looks, but it is a nuisance. In the end, using that formula, or secret tricks...
Oh, yeah, I mean, obviously I can see where everything is zero.
Need to subtract the products of the diagonals. But what about a 3x3 matrix? These sorts of determinants can be
Because
calculated...
it fully mixes. It fully mixes. Like if I were doing it like this, I see that A is here, and then where A is not present, D is present, and then where D is not present, G is present. So it would just be a 0 would be included in every single one of these terms and make it all 0.
This snappy formula,
Sticky notes slob. I think these are just cutouts.
As bad as it looks,
This is cut
but
paper.
it is a nuisance. In the end, using that formula, or secret tricks if you know any, we arrive at these solutions. So yes, solving a dog wall problem, or dog frog wall problem, or dog frog smoky prog wall problem should be trivial for a math PhD haver. Evan was almost certainly joking about every part of this tweet. He's only 21, so probably no PhD in math from Oxford. But just for kicks, what does it take to earn a math PhD from Oxford? Well, certainly a whole lot more than we could touch on here. But from 2007 to 2025, although this diagram looks like a giant mess, the information we actually need is rather simple. And
Wait.
math from Oxford. But just for kicks, what does it take to earn a math PhD from Oxford? Well, certainly a whole lot more than we could touch on here. But from 2007 to 2025, if you are a student in the 4th term of your A-levels, think the end of high school if you're in America, if you wanted to be admitted to Oxford's math program, you'd take the MAT, the mathematics admissions test, to demonstrate the depth of your math knowledge. It has now been replaced by the TMWA, but in October 2025, there was a final MAT test. The test consists of 25 multiple choice questions, and then some so-called long questions. The long questions that a student receives are either version X or version Y. So let's take a peek at a couple of the, let's say, version X questions before we part ways.
I was going to read it out. I don't know why I'm
Parts
pausing to read it.
1, 2, and 3 are with respect to a diagram described here. Parts 4 and 5 are with respect to the diagram that's described here. And if you could solve that dog and wall problem, then maybe you could solve these too. For a bit of fun, let's try the first and last problems together to see how we might do if we were trying to begin a journey studying math at Oxford. So the first question is about the number of segments in the diagram that's described here. It says there are 8 points equally spaced around the unit circle, with each pair joined by a straight line segment, except for the cases where the 2 points lie directly opposite each other. So if this is our unit circle, and these are our 8 equally spaced
How
points,
many line segments?
here is in red the line segments that aren't included in the diagram, because these are the ones that connect points directly opposite each other. You can see that's a total of 4 line segments that
That's a weird way to count it.
aren't included. Then, to answer the question, how many line segments
I
are
would
there
literally
in
just
the
draw it and count it.
diagram? It's
I'll explain your
easy.
answer.
We can use what's called
Can I
a
not just say I
binomial
drew it and counted?
coefficient to count them. In our case, we need
Okay.
n, the number of points, to
Yeah,
be
that's
8,
what I was. Yeah.
and r, the number of things we're choosing, to be 2. This is read as 8 choose 2, and it tells us the number of
I
ways
never
that
remember
we
this.
can pick 2 points from our collection of 8 points. And the question says that any pair of points is going to be joined by a line segment, excluding, of course, these 4 line segments. This is essentially the total number of possible line segments, which is 28. We know from the question 4 are being excluded, so the final answer then is 28 minus 4, or 24. The last question is a bit trickier and concerns a much messier diagram. We could draw the diagram and concern
Yo, what is this? Just watching YouTube now. I'm doing research. Day 30 of Crawlerbot. I have apparently stumbled onto, like, I would think it's probably called an NP hard problem. Balancing a rigid object on any 3 points. How much force do I have to apply to each point? There are infinite solutions. And a lot of those, and half of those solutions include negative force values, which is non-physical. So
a much messier diagram. We could draw the diagram. It says that we have 3 sets of points. A, which has 3 points, B, with 4 points,
type up
and
a Claude
C
prompt
with
I'm going to take
5
care of
points.
you. Here's what it's going to do. It's going to give me a stupid answer. It's not going to give me an answer. It's going to give me an answer for a much simpler problem than what I described. Or it's just going to say, here's the equations you need, good luck. And then the equations are just a system of equations that I already know exist, and they still give me infinite solutions.
And
Oh, do an iterative approach, do gradient descent. Like, that's what I'm trying to do. But
every point
there's a very intelligent way to do
in
it.
each set is
If you're specific, you can unlock the intelligent version.
joined by a line segment to every point in the other sets. That means that although this diagram looks like a giant mess, the
I can write it as a set of equations, which I think is what I did, and then I looked at it and I'm like, I can't solve that. The models respect you if you speak to them intelligently. I just wanted to watch the rest of this because I got kind of excited with the determinant thing, and then I saw this. I saw these 2 diagrams, these 2
behind
graphs
each equation
he threw up here,
represents
especially this one because I was trying to visualize this. was like, oh, maybe I can do it with that. Nope. A determinant can't
A,
have
which has
zeros.
3 points, B, with 4 points, and C, with 5 points. And every point in each set is joined by a line segment to every point in the other sets. That means that although this diagram looks like a giant mess, the information we actually need is rather simple, and perhaps would be
Your
better
brain is not capable of
represented
understanding multidimensional matrices? Yes, it is.
with this simple schematic.
Yes, it
Here
is.
are our 3 sets with 3, 4, and 5 points, and the lines between them just represent the fact that every possible connection between the sets exists.
That's not theories in computers. Oh, and you can't understand this? Put 3 fingers on this object and don't let it rotate. How does the universe know? How does it know? Like, you don't even have to think about it. Just, like, literally set the object on 3 fingers and it just doesn't rotate. I mean, maybe you have to, like, reposition, like, get a, you know, a point starts dropping, so you're like, oh, let me move my finger over there instead. I mean, that's part of it, but... like, draw a triangle. If the center of mass is in that triangle, wherever you're holding onto the object, it's not going to rotate. Check how many legs are touching a wall, and if it's greater than 3, it holds on. I need to apply a force back to the ground, which means I can't cheat anymore. I can't simply say each leg is going to apply anti-gravity to the center of the body. It has to apply anti-gravity at that point on the leg. Or at the very least, it has to know how much to apply back to the ground. It also causes rotation. Even if I cheat and I just lazily say, oh yeah, 33%, 33%, 33%, it's going to spin. It still spins. So I have to give a real answer. If I slap it on the wall, it picks up 3 legs, it's going to start rotating. Cheat more smarter. I don't think I do. I think I just solved the problem. I have a solution in 2D. I mean, sort of. Does even run. Wait, how do I run this? Okay, so this one's balancing. Maybe it's a little bit hard to understand what's happening. It is rotating constantly, but these 3 points are supporting it. It's not falling. So it maintains its current rotation, but these 3 points are not adding any more rotation. These look like good solutions, right? This blue point has about 60% force, and these 2 points have about 20% force, right? 0.6, 0.2, or 0.6 plus 0.2 plus 0.2 is 1, right? The problem is as I let it continue to rotate, this happens. I end up with negative 24, negative 12, 38. Like, these are... what is this, right? I can't have negatives. I can't have a value over 1. That's not allowed. So I have to have a smarter solution that doesn't let that happen. Sounds like your math is wrong. It's not wrong, because look at it. It doesn't fall, and it doesn't add rotation. It keeps a constant, consistent turn. There's even a breakpoint in here. There's even a breakpoint here. If the angular velocity is ever not equal to 5, it stops running, which means this is a perfect solution. I'm calculating a perfect solution in real time. It's just the problem is sometimes the solution that my thing pops out is negative, or values go over 1. Not the wrong math. it is the wrong method. Which this is really fast. I do have like an iteration here. I don't have to do that. I think leaving this at 1 is sufficient. It might not be sufficient. It might like actually fail. Oh no, I calculated instantly. CPIN, yeah, I see it because I already read the message. Right, so in a single calculation, a very simple calculation, I can compute force values that work. But they're not physically accurate values. They're values above 1 and they're negative. And plus, I think even my current solution does not extrapolate to 3 dimensions well, because in 3 dimensions there's a lot more room for instability. Points could be aligned such that they don't enclose the center of mass well. Or that will happen. Points will be aligned that they don't enclose the center of mass. Which means I have to apply the best solution, which is going to still result in some rotation no matter what. I have an additional dimension now. Technically it's 3 dimensions, but it's really just 2 dimensions because yaw is always 0. There's always a 0 in the middle. So it just pitches and rolls. Rotation is really silly. I wonder if because it's in 3 dimensions that this like actually stabilizes. Will this ever become stable on its own? I think it would if I applied angular damping. What if I did that? It actually is stabilizing. I probably could have increased the angular damping. I can probably increase it. There. Does it really need more than that? Alright, this is basically not changing anymore. Okay, so this value is canceled out. Wait, no. Wait, how does that work? Oh, wait, this is the same one. No, this is not. This is like a much smaller one. All right, so these two cancel this one. And this one cancels these two. Okay. Is this like really... What is this question?
Sets of points. A. Next question is a bit tricky.
The thing that caught me here was loop. There's a term with vectors. I don't know if this was exactly right, but it's basically like closed loop. Add one vector, add a second vector, add a third vector. You're back where you started. That's pretty much the same thing that I'm doing here. Add one angular velocity, add another angular velocity, add another angular velocity. I'm back to where I started. I didn't make any... I had no net change. Actually, I want to go back to this one. Because if I actually think about it, I could pick, right? My constants don't really have to be 0. I could say this set is where I'm trying to go. What do I have here? So this number plus this number would equal this number. So I pick this as my constant. I pick some value as the constant, and that becomes involved in... Yeah, pick some value as a constant, right? And then these two become... So it's the case that a coefficient is a coefficient and a constant. So it's all right. We have to cancel this one out with this set of points. I mean, I'll just assume for a second that this isn't even already a stable solution. But I would look at this and I would say, all right, I have a negative value here. This negative value has to be canceled out, or all the negative values have to be canceled out by all the positive values. Right? So I look for that solution. And then I say, all right, well, I found... I mean, I could just kind of do that, right? I find that number. And then I look through here and I say, all right, here's the negative value. This needs to be canceled out by all of these ones. So now, what set of numbers do I need to do that? And then I take those two sets of numbers and I just somehow combine them. Somehow. And I guess I would do the math for the middle pair anyway, but it would probably just see that the total is already 0, so there's nothing to cancel out, so we just ignore that. use some kind of signal value that says when I go to mix them, disregard it, don't try it, don't blend this one. Alright, so let me just start with the very first frame then. What's the very first frame? What would I do there? I have this value. So I look here and I say, all right, this value needs to be canceled out by these two values. So then I calculate what the factors are for here. If this was 1, or for this one to stay the same, what would these two have to be? And then this one would be canceled out by these two. So for this one to stay the same, I guess how do I pick which one stays the same? I don't know. I probably pick the one that has the highest value, I guess. And say, all right, that one stays there. So out of this, I mean, just eyeballing it, it would look like roughly half. So this would be at 1 and these two would be at 0.5 of their value, because it looks like they already nearly cancel out on their own. So I just cut them in half. And then I would look at this one and say, I might even say that this one looks like it's perfectly canceled out. So this would just be 1, 1, and 1. So out of my two sets of numbers, I would say all 1s and then a 1, or it would be all 1s and then a 1, 0.5, 0.5. And then somehow I blend those two together and see. I mean, maybe that's it. Maybe that's it. Okay, I mean, I guess I'll look at it. So, calculate forces where all this stuff happens. So I get the rotations. And then I'm checking the axes. So I'll say I'm going to have a collection, a set of three values. What am I trying to say? It would be like a matrix where the first row is as long as the number of points there are, and I have as many columns as there are dimensions or degrees of freedom, which in this case would be 3. So it would be a 3 by 3 in this case. How? I could just use an array of arrays, I guess. I don't know. I mean, it could be a packed vector 3 array. I could just do that. So each point has how much it shares for that degree of freedom. Or I guess each blend. So what I do is I would run through this 3 times. I guess we'll call it axis. 3. So I will find the largest absolute value in the index. Well, I guess I don't really need to, I need to know the value. I mean, I guess I can calculate it. I could use 2 vector 3s and just check every single one every time. So I'll flip this around. That'll be a vector 3i. Okay, so I find the maxes. And then yeah, I guess if I don't find one, then I know that's already 0. I guess this was the case where I don't care if they already balance. Well, no, I calculate it anyway. But if they already balance, then the results are just a set of 1s, right? Move this down. And my idea here is that I find they should converge. If there is a solution at that point, the value should converge to something. I won't allow anything to be negative. I will disallow the total from exceeding a certain value. So if it says, yeah, we can cancel this one out, but only if these two are at like 0.5 and this one's at 30 or something, then I'll say like, okay, well, drop that 30 down to 2 or something, or whatever the max value is. Okay. So now I have all the maximum values. I have the one that I'm balancing against the other, all of the others combined. Is that right? I mean, maybe, yeah, maybe it is right. I take the one that has the highest angular change. So on, oh, no, I'm looking for the highest absolute value. So I just do that. Okay. But when I say I balance it against all the other ones, I guess if it's the highest on that axis, then I know that any other one with the same sign is going to be a smaller value than it. Is that the right way to go? Let me try to think about what the result of this might be. My idea is that the result, geez, could I say a word? The result might be to favor the points. Favor applying more force to the points that create more torque. Which sounds like a bad idea. I kind of want to do the other way around. I want to favor adding more force to the points that don't add torque. Or rather, sets of points that, when combined, already cancel each other out well. Which kind of makes this like a combinatorial problem very quickly. How many groupings are there of 3 points without having at least 2 groups and no empty groups? So it'd be 1, 2. I mean, I guess let me think about that. Or let me write it down. Would be A, B, and C, A, C, and B, B, C, and A. Oh, is that it? Wait, there's actually only 3 options? Okay, so with 3 legs, I guess I could explore that. I would start by finding which pair counteracts the other, the single value, the best. And then I guess there's also this option. But I kind of don't really know what to do with that one. Because that just goes back to... What would this do? If 2 legs already cancel each other out pretty well, and one of the legs takes on very little force, or does very little change, then what would that mean? In that case, I would take, let's say that this was the best setup. I mean, I guess I can apply that here. Which one of these does very little force on an axis? So this is very small negative, and these 2 already cancel each other out very well. So what I would say then is this point, so this would be like A and C. Let me step through this and see what that result would be. Or imagine what the result would be. I'm just going to get rid of the zeros because they're 0. And then I'll shorten this out. I'll round it off to 5 places. Okay. So if this was A, B, and C, and maybe it would be better to look at it because at least here, then I can line them up and I can see, oh, this one has the small value there. This one has the same but opposite value there. Right. So yeah, looking at this, if I were to go through this method of checking exclude that one, checking 2 legs against the other one, I would say that A and C are well countered by B. So I would inspect this combination. This would be like a starting point. So I have like 2 values I'm solving for, which is easier than solving for 3 at once. On this axis, specifically. I mean, I can just do the math as well. So I'll see what the total result of this one is. Just add them all up. Okay, so the result is that. That would become 7. Okay. So this is my total, and this is kind of what I need to balance then, right? So overall, it's a negative rotation. So then my thought would be to go and look at, because they're set up in pairs, I would know which one of these is the positive pair and which one's the negative pair. So I guess it would kind of be like B minus AC, because those are the signs, right? So I have a negative value here, so I say, all right, I need to go balance. I mean, I guess then I could even say, all right, well, here is the offset that I need to apply. Who has the largest value? I guess because I know that the result was negative, that means the negative side has too much force. So what would I do? I would want to evenly split that change. So I'd want the negative side to get a little bit weaker and the positive side to get a little bit stronger, but in equal proportions. I mean, yeah, that's the only solution that makes sense. So I would say decrease negative side, increase positive side. So I do already have okay, so this is the current state. This would be like 1/3 to 2/3, right? This is the current split between these two. And the idea is that man, I have to like go look at the math I did for the other one. So what I do is I take that rotation over the force, which is like a normalized value, and then I take that force, that result, subtract the sum, and divide it by that. And then I do this. I take the original force and I add the original force times my calculation minus 1. And that gives me, I think that's what gives me the perfect split, right? Though I'm still skeptical about this. This seems like I wasn't quite able to follow it, I guess. I wasn't quite able to follow the intuition of like, I'm doing this step because this is the physical analogy of doing that step. So I guess my thinking is, what would I do here? If I know the current split is 1/3 to 2/3, that's just like the initial default state. I mean, I guess I don't really know that this is what it is. I mean, that is the current state, but there is a different way to do that. I would say, here's the sum. I ran through all the calculations. I found that this was the value, this was the pairing that was closest to 0. So I wanted to start there. I guess the question is, if it's closest to 0, I start there. Why do I start with the one that's already nearly well balanced? Or why do I start with the one that is the most balanced already? I guess maybe it's similar to what I just said before. Or if you have a random object in your hands and you set your 3 fingers and you place it on there, and the first thing you notice is it starts to rotate some direction. I didn't even think about it, but I said the first thing you would do is you'd probably say, all right, well, I see which part is falling. Let me put some stability under that part. So maybe I don't start with the side that's the most balanced. I start with the side that is the least balanced. And balance that. Which means I find the pairing of points that gives the largest absolute sum. And I balance for that one first. So looking at these, which grouping is probably the worst? Balancing. I guess really it's kind of the idea that I just add all these together and I see that, oh, well, this equation's already well balanced. I add this one again and I say, all right, this one's really bad. So it would probably be I mean, I guess any grouping, if I look at it, yeah, I just find the one that has the worst sum and I balance for that one first. I think that actually makes the most sense. I start with that one. Which means I don't really end up with a pairing. But I guess I also kind of get that at the same time. So I know that this one would have the worst pairing. And I'll write it out as the positive signs first and the negative signs last. So it'll be A, B, C. So it'd be these values added together. This one must be the worst. And this one is like the exact same value duplicated, so I'll just... that, okay. So this is sum. So I follow the same path from there though. I say the sum is negative, so I want to decrease the negative side and increase the positive side. Decrease the negative side, increase the positive side. So what would I do then? So I guess what I say is if I were to place this point on the number line and this total on the number line, I guess let me even find out what that is. Negative 0.4026. Which oh, I copied. Yeah, okay, I see now. I was like, how did I? That plus this one. But I would find the midpoint. So it is this divided by 2, as if we were on a number line. So I would add this to this combination and then add it to this combination. Wait, what? Decrease the negative side, increase the positive. Not add. I would subtract it. So I would take this value and subtract it from both sides. So I would say this minus that. So I'd say, all right, I would like the force on this side to be this value. So new A would be that. And then new BC would be I mean, I guess I could just do the calculation one time and I know that would be right. So this is what I would like the forces to be. So what share of force would give me this? So I guess it's just kind of saying, what do these multiply by? So the result would be this value over the original value. I'll just round this to 5. I guess this is more like the share change. Round that to 5. What is it? It's the new value over the old value. You can multiply the forces as new over old. So whatever the force of A is, in this case, I want to multiply it by this. Whatever the force of BC is, I want to multiply it by this. So and then I think this is kind of okay. This is where this comes in, right? So I do forces plus forces I times that value minus 1. And then that's the correct value there. So I guess I guess I could try both ways. I can see what the results are. So apply the change. Method 1, multiply and rebalance. Method 2, add the change of rebalance. So I'll just start with multiply and rebalance. So I know that the overall force in this case would be 1/3 and 2/3. So I'll just multiply it. So do 1/3 times this value. That's a 5. And then I would rebalance that. So just take these two, add them together. And then I divide each one by that value. That's my idea. Bro, what are you saying bro for? Is it hot there? In my room it is, but outside not really. Yeah, right, so these kind of, yeah. So I'll try 4. Okay. So there's also another part in here where the question is, how do I split this change between B and C? And in the case where 4 legs get involved, how do I split that change between 3 or if there's 5 legs involved. How do I split that change between all of them? I would want to do it where the values that have the highest impact on Angular, they'll kind of scale proportionately. So if one has like literally 0, its force will not be changed. I literally won't touch it. If one is like 0.1 and the other one is like 1, then the 1 would get changed by, I guess in that, there's definitely correct math. What I'm going to say is definitely wrong. But the idea is that the 1 would get 90% of the change and the 0.1 would get the 10% of the change. Something like that. Or I'd add them all together, so it'd be like 1.1 is a total. So it'd be like 91%, and then the 0.1 gets less than 10% of the change. That kind of thing. But make sure I do it in a way that, even though I've distributed the force change, the multiplication still works out. It's 8 p.m. there? Yes, just about. And I would say this is the hottest time of day in my room because of where it is. So that's normalized. Okay, so I just want to say that one sounds fine to me. I feel like that method makes sense. But there's this other way to do it. Maybe it's literally the exact same calculation. I don't know. So I'll say old force plus that force times the change minus 1. Okay. This is what I was hoping for, is that these are just the exact same result. But I guess I just wanted to be sure that that was correct. That it actually would be the same result. And that's not how that works. Oh, wait. Wait, it's supposed to be 1. No, yeah, it is that one minus 1. Okay. Five, 2, 3, 8, 1. Repeating. All right, so I don't have to do crazy math there. It's the exact same result. Okay. Apply the change. Multiply. I guess it is like normalizing, right? Or no, I divided by the sum. What is that called? I don't know what that's called. Divide by sum. Okay. So now the final step is I would distribute whatever the change is among. I distribute this among the other forces, and the other ones based on the absolute value of this one. Distribute new force total onto using the proportion of the max in the group. So in this case, A is really easy. Because there's only one, so it is the max, so it gets that. So now it would be A would just have for that repeating. And then B, so in this case, damn, it's actually kind of annoying because it is already, they're already shared. So originally it's 33 per, it's 1/3%, 1/3% on both of these. Not 1/3%, 33 repeating percent. But what if it was like this one's force was, okay, I have an absolute amount to distribute. But I need to distribute it such that when I remultiply the values out, I still get this value and sum them together. So I can think of it as saying, I don't know how to really. C times FC is negative right. And then I have I'll be back in a minute. I'm back. Okay. I'm just writing it all out. Where's F? Where? Wait. No. The old one was this value. The new one is this value. And I want the new one to be this is not going to be equal to this value. And then I want to be equivalent to, I think I've said that I want it to essentially be like some sort of proportion here. So this one, I guess I'll just say FB used to be, I know it's not exact, but it's like that. I mean, I guess I just do that. I don't know how to write this out. I guess I just do the math. I know that these are shared too, which actually really sucks because they're shared. No, not like that. It would be like this value times I'll say b, if the angular b over the max, the max angular, like that. But it has to be shared. So it's like a third times, yeah, it's a, So if it is the max, it'll get the most change. But I think it's not the max. I think it would have to be the sum. So it'll be this over the sum. B over the BC angle. So it would be like, this would get half of the share. In this case, it would be half, right? I at least have to set up so that if they are the exact same value, then they both get half the share, right? So this now becomes 0.5. I mean, I guess would actually just be this, wouldn't it? Force new is this times its proportional share. But then I think it's not. That doesn't work then. So here's what I'll do. I'll make the sum of these, I'll keep the sum the same, but I'll make them different values. So I could say I'll do add 0.08. So I'll make this. I'll pretend like this is the new value. So this is B, and that I added 0.08 there, so I need to subtract 0.08 from the other one to get this one's value. Okay. And I feel like this is where it's just not, that math isn't going to work. Because there's a more appropriate way to, I think at least. I guess I'll find out. Maybe I write this in a better way, where I say the force of n would be equivalent to, maybe this is where I set it up. It should be this proportion of, the ratio between these two should be this ratio. I mean, this is what I think, but that's not exactly, no, I can set this up. I think what I mean to say is that it's like a ratio of these two. The change in this one is proportional, like I said, to a change in another one by some fraction. And this is the fraction that I'm kind of looking for. But I can't write it out because then I'm like, solve it. I know that I have this, right? Adding them together, I get that value. Adding these together, I get that value. I think this is it. So the change, so FBN over FB, I want it to be equivalent to a change. How do I write this as a change? This? That? So now this is a change, the ratio of the change of its original force will be equal to but am I setting it up right? Okay, so let's say I go from 1 to 0.8. So it's be 0.8 minus 1 over 1. Let me maybe do a better number. Let me say I went from 0.8 to 0.5. So what does this mean? This means if I took 0.8 and I multiply it by 0.1 minus 0.375. Right, okay. So the percentage change is equivalent to the B angle over BC angle. Is this solvable? And then the force of C minus force of C over force of C is equal to C angle over BC angle. And then I have this restriction, right? And then together I get this value. Add this together, I get this value. I mean, I guess I can just work this out and fill out the constants and see what I can come up with. So I know that B. Well, I guess I actually don't really know what B is. Okay. So I think in this case, this is where I would do. I guess this is the case where I can say B over FB times that, and then C over FC is this. Huh. Okay, so in this case, this is where I've gotten like a normalization of it. I have how much angular do I apply per unit of force, basically. Angular per unit of force. So I can figure out what that is. It would just be this value over a third. Which is the same thing as doing this value times 3. Okay. Move these up here. I should do all this really. So here's all the set, and I'm looking for the unknowns FBN and FCN. With all these restrictions. I'll just drop that one. I'll put in the constants. So I'll see what I'm getting. If I can sort of simplify it out. I mean, okay, so here's kind of an issue. This one already gives, I think, a solution. I think there is only one solution here. Right. Well, I don't know, maybe not. Maybe if I ask it to solve this, it might tell me no. Solve. Ah, it's a line. Okay, so I actually do have a lot of choices. There are a lot of choices there. Okay. So I have a line of choices, and I can pick any proportion that I want. Effectively, any proportion that I want. Right? The maximum for y can be 0.4. The maximum for x can be, what is that, like 0.75. I guess the problem is, can I really select that? Can I select it like that? All right, but the B angle, which is actually just B, B over B plus C, C over plus C. Okay. I guess the thing is I can solve for either one of these. So I just pick one. So I guess I'll just pick one and solve it. And then I know that the addition of these two... I guess I actually don't know the addition of these two. Okay, but I'm getting weird math there, so I'm not going to bother with that. So it'll be this. I know this value is 1/3. I guess I won't write that out yet until I get it reduced. I guess I can go ahead and do this math. I mean, here's the thing. I can pick one and get the right solution. But I guess the question there is like, which one do I pick? Because I just picked 0.34. Which if I go to here, I know that 0.34 exists in two places here. But I guess the question is, which 0.34 do I want? I would like y. I think I just said that y would be 0.34, which would be bad because then these are... They seem a little too unbalanced. Can I grow that? Oh, thanks. Cool. I can't zoom on a graph. All right, just copy this graph. Plain text. Then I can copy it. Sheesh. Get rid of these lines. What did I just calculate? Oh, no, that's actually not the value I calculated. It's a little bit different. Round this to 4, or 5, I mean. 9. So if I multiply both sides by FB, and then I can add FB to both sides. So I could say FBN should be, in the original FB is 1/3. Which seems weird, now that I think about it. But I can just copy this and paste it. 0.442 for B. When I ran this, B would be this one, X. So I said X should be 0.443. I mean, I guess I could also pick the point that intersects the Y. No, I wouldn't want to do that. I want it, yeah. Does that ever not work? Okay, let me... This one increased in force as a result of this. This side decreased, but this one increased. Yeah, it doesn't seem right. This one's force increased. I would want the other one's force to increase and this one's force to decrease, is what I would want. So I calculated that point. So I guess let me see what the other point would be, because there's 2 points where this works. If I calculate for FC instead. But this side would just be the exact same. It would be C over B plus C, which I got rid of. And 5, 5. Which is not an option. That would give a negative result. Okay. Interesting. I mean, maybe what I can do is I can plot... I mean, I guess what I'll do is I'll plot this equation, right? I would plot this equation. How can I make this an equation? And then get the intersection point. Okay, so where do I think it should be? So if the x-axis is B and the y-axis is C, I would want C to end up... I want them both to reduce. So I guess I could say this. So where is y less than 1 over 3? And greater than 0. Right? So here's like the band. I need them both to reduce. I guess it's more like there's a... And x is less than a third. It's more like x plus y is less than 2/3. How do I map this? What? Oh, maybe it's where I just say like y is less than a third, where x is less than a third. Right, okay. So this is the segment of the line where they both decrease. I don't know, but I guess that's a case where I don't necessarily want to decrease. Yeah, I mean, how do I pick where to go on this line? This is the portion where they both decrease. And if I said x is b, y is c, right? Yeah, y is c. So I'd want to maximize b and minimize c, I think. Which would put me here. I would find this point. But how do I know this is the region I'm looking in. I mean, I guess what I can say is say that, I don't know, like what's I don't know, what's x over y? X over y is equal to this over that. So just find the point where these intersect. There's that 513 intersection that I think I found before. Okay, it's not. And then I can do this, and then I have the proportions. So I would say if x is b and y is c. Okay, this is the wrong way around. Do I say it's inversely proportional then? I'd make this y and make this x. I don't know, maybe that's what I do. What was this one? Yes, it's solve this, and it gives me this line, right? Which must have some solutions. Some positive solutions. Right? I mean, it just obviously has to. And because of the shape of this line, it's guaranteed to intersect at a positive solution as well. Are these the inverse of each other? I said this was x and this was y. Okay, maybe I don't know how to make an inverse of a function. Or like the mirror of a function, or whatever I'm trying to say. Because these lines just look like they suspiciously have nearly the same slope. If I multiply each side by x. What is this proportion? Four, 8, 9, 6, 1, 6. That's the same number. But then there's this plus. What was this plus at the front from? Where did that come from? It came from that value. Okay. Okay. So I think what I have instead of all this junk is that x over y, what was it? It would be the smaller over the larger. And if these were both these would be the same sign, but if these were both positive, yeah, it'd be the same way. Because of how... So is this the ideal solution then? X becomes that. Can I just write it out? Oh gosh, please. If I just write this out like that. The line still stays. So I'll say A is equal to this value. I'll say okay. And then I have y equals b over c. I think this case it's like the min b and c over the max of b and c. Okay, so what did that line just change? Huh? Oh. I meant, yeah, the absolute value. So because they're both negative, it would actually be the other way around. Right. So, wow. All right. So as I mess with this line goes down. What is A? A in this case is what I need it to be. So if I need it to be 0, it would just intersect at 0, right? They both turn off, right? Okay. All right. But as it, whatever it is, okay, so this always stays above. That's good. Right. B. These go out like that. Okay. Yeah, in this case now I do see the problem. I'm getting a solution that's kind of insane. I want B to become greater than that. So that function doesn't quite work. It works when they're close together, but once we cross this point, then it's bad. And you know what? It kind of doesn't make sense either, because how do these two numbers add up to that value? They don't add up to that value. So hang on. I'm missing a restriction here. Yeah, the restriction I'm missing is that x plus y must equal this value. So that's this line. Which in this case, here's an intersection. So disregard that. Here's the intersection. So I would say B must be 0.28 and C must be 0.25. So there's actually just one choice. But is it guaranteed to exist? It's not guaranteed to exist. Okay. It could not exist. There could not be a value for it. If this value is too close together, it also fails. It goes into a negative. The lines don't intersect here. In fact, if they're the same value, it's not possible. What does that mean? A value is not even possible. So these are all the possible solutions for that. Well, I mean, it's not that they can be parallel. I'm assuming they become parallel when these two are the same value. Or something like that. I'll just zoom out to see if these two lines ever intersect. Yeah, I think they don't. Right. Yeah, I mean, if I really think about it, this is just the equivalent of this minus x, which means it's a slope of -1. Starting there. So... yeah, then if... Yeah, so... Man, wow, okay. So it's kind of like a real solution is not guaranteed to exist here. times x plus c times y equals a. If these two lines intersect, it's stable, right? But it's possible for these two lines to not intersect. Or to give really bad values. Like this. Where one kind of has stolen from the other. And I think I don't want that to allow that to happen. But I do have this other line, technically, that exists, that is sort of guaranteed to give me a solution, even if it's not perfect. This line. Oh, I already have it plotted. This line. So I kind of get two solutions here. I get one where the forces match out, but the proportions are... Sorry. The proportions are good, but the resulting force is bad. So in this case, B is high, C is low, but I'm assuming... Is there like a way to get the intersection points specifically? If I made all these lines have like a formula. So you can say minus a. And then I have to extract y from this somehow. Huh? I can do minus a. I can subtract c times y. And then I can divide both sides by c, negative c. Okay. And now I have it as a plot. All right. And then I can say this one would be m1 of x, m2 of x. So what happens if I do like f of x is equal to m1 of x? Okay. It just says, cool story. How do I get the x coordinate for this? I set them equal to each other, and then I solve for x. So if this is m2, How do I do that? I feel like there's got to be a way to do that with Desmos just to get the number out. I don't know. Whatever. Right, okay. So I get this line which tells me the point of intersection between M2 and F. Whatever. So I guess what I have is the white line is oh no, the blue line is my ideal. So I want to intersect on the blue line. If I intersect on the blue line, I'm fine, right? I'll be fine. So I can sort of guarantee that M1, I can definitely guarantee M1 gets me a valid solution. I cannot guarantee that M2 gets me a valid solution, which it's okay, it's sort of two things here. I can guarantee that this gives me a solution, a positive solution, but it could be a solution where one of the values is greater than 1. Or I guess it lies off this. Okay, I think what I'm really looking for is these two lines. Or is it like ideally it would be where these two lines intersect. Right? That's where these two lines intersect. Maybe what it is that I'm seeing something here. Because in this case, I have this like weird triangle that's formed. I've made a triangle. What does this region represent? This region represents a bad share of the force, the allowed force, so it's bad. It's above this line, so it's actually going to end up applying more force than it's supposed to, which will cause a rotation. Below this line, will apply less rotation than it's supposed to. So I want to be as close to this line as possible. Wait, no. Sorry, I was wrong. The blue line is that. If I'm below the blue line, I'm not giving enough rotation. I'm not stable. If I'm above the blue line, I'm too much rotation, I'm not stable. So I want to be as close to the blue line as possible. If I deviate from the white line, my share of force is unequal, which means I'm going to have the result of I'm either applying, I start stealing too much force away, which means it's going to be unstable. Or if I'm below the white line, then I end up giving up some amount of force, which again will make it unstable. So I want to be as close to these two lines as possible. The ideal solution, of course, is wherever they would intersect. I just pick where they intersect. So I could say, if these two lines have an intersection, I just use that. That's like the spot. That's the spot. This happens to have the result of giving more to, at least in this case, kind of lock the viewport. This has the effect of giving my desired effect, which is giving more to B than C. Because you can see B is 0.28 and C is 0.25. That's what I would like the result to have been. And where is that true? Trying to see where it crosses. I guess the cross is somewhere over here. Well, I guess I can see exactly what that is. I could say where, huh? Are you not happy about that? Whatever. Okay. I guess it would technically be anything below this point, which is, this intersection is barely in that range, but whatever. If they don't intersect, which would actually be the case where these two already had the same amount of force, and they were supposed to be sharing it, I still want to be on this line. Is that really true? Am I thinking about that right? What is X here? X in this case is the amount of force that I apply to it. Huh? I mean, I don't know. Is it the case where these would be like, what? I don't understand why these two lines don't intersect, honestly. I feel like they should have intersected. Maybe I've just done something stupid and I'm not visualizing it correctly. I mean, maybe that is true. There's only one distribution of this force where they will also be on the blue line. But then this line represents my ideal. This is where I would like I would like the distribution to be made like this. I want B to get the most and C to get the least. Which in this case actually drives up B and drives down C a lot. Because C has a very high, in this case C has a very high angular rotation applied to the body. So I want, my ideas there is I minimize that. I'm trying to minimize it. I could exactly minimize it by just making it 0, but that'd be stupid. And the closer I get, the closer I am to these two lines, the more stable a result is. Ideally exactly on the intersection. That is right. So my wonder is, so what if I pick the intersection point of this my choice line with the proper distribution of force, and the intersection of my distribution with the force that would actually be stable. But like I said, because these two are far apart from each other, on this part of the line, we are applying less angular rotation than we want to, because we're below this blue line, which means it's not stable. And then on this blue line, we are taking extra force that we weren't supposed to be taking, which has to take away from the other side once we normalize it. Which means this will be applying more rotational force and the other side will be applying less rotational force, so I'm less stable there, right? This could even make it worse if I were to pick this line. What I could say is I pick the midpoint to minimize both these effects while keeping my desired choice. Or I could even say find the midpoint of all three of these points, which would probably be like somewhere over here, and use that. So that would result in I'm taking a little bit more force than I'm supposed to. I'm applying a little bit less rotation than I was meant to. But I'm also close-ish to that. I mean, ideally, like, all three of these points intersect the same place. Perfect, right? You know, what about this case where the midpoint is somewhere way out here in like crazy world where I'm applying 4 force to one of the points? I mean, this line still intersects here, which is, you know, the white and the blue line is perfect. That's what I should pick. I should favor being as close to that intersection point as possible. Then I guess there's, like I said, it's... I think I will arrive ultimately at a better solution if I am maybe a little bit closer to this line. So the midpoint probably doesn't work because the lines could have an extreme slope, and the midpoint would be unrealistic. In fact, probably being between these two lines might even, in a way, cancel it out, because when I take more force but I'm applying less rotation than I'm meant to, maybe it's something that just balances itself out, or like very nearly balances itself out. So if I was on the line that was perfectly between these two, I mean, I guess I could plot what that would look like. And then maybe that's what I do. I find the intersection of... I create that new line, which is the line that is just halfway between... Yeah, okay. No. The blue line on the Y line. So maybe the idea is that this is my probably very stable line. And I might pick this point. Up here, it would be I'm taking less force than I meant to, but I'm applying more rotation. So maybe it cancels out. Then here, I'm doing more force than I'm supposed to take, but I am applying less rotation than I was supposed to. So maybe it works out. I mean, maybe that is an idea. I take the intersection of my orange line with this pink line. Because they should always intersect. I should be guaranteed to get a solution there. But also, something interesting might be happening. Ooh. Something interesting is happening. Kind of guarantees that the solution, as long as C is greater than this one, I would have to flip it around, flip some things around. But because of how these lines can intersect, this can't ever return a value greater than 1. It can return a value that is a much higher use of shared force than it's supposed to, but huh. Okay. Here's one. I could say that. What did I say? What was that equivalent that I said? It's what, the orange line? Yeah. This is where the forces match the proportion. Which I guess that's not really what I'm looking for, is it? That, yeah, that's still not exactly what I'm looking for. I'm not looking for the forces match. I'm looking for where the change that I apply matches their proportions. which yeah becomes the change that I apply matches this. So what? I already have this plotted. I don't have that plotted. Was this one that I said to solve for? No. I don't know why I deleted it. Let me write it back out again so I can. Yeah, why did I get rid of that? Yeah, that's the weird part. When I see that the new force is equal to the old force plus some plus this, that's a weird thing, right? Would it not actually be the same as doing 1 plus FB would be like adding 1 to this? Is that right? So yeah, there's this value. Which on the yellow line, yeah, it's this is a pretty far value from those other ones. I think I'm gonna wrap it up here soon. Yeah, like why does it come out to be the plus like that? Maybe that equation is just wrong. That's probably what it is, right? That equation is just wrong. I've plotted it wrong. Not plotted. Why'd I get rid of it again? Because I know that the new force should be less than it was before. Oops. But the formula I've written out is not doing that. So the change as a portion of its total should be equivalent to the other thing. I don't know if that's right. Because if this value is less than that value, this would end up being a negative value. Would be equal to a positive value. Yeah, that's not correct, right? If I know that this should be a negative value, then it's wrong. Or, sorry. If this side would be a negative can't be equal to positive, so that's how I know this is wrong. Maybe it's more like what have I said? It would be like if it was 50-50, they would share it, right? They would share the reduction, which would mean yeah, I gotta wrap it up. I mean, I guess it would be like times 1/2, right? Which could be like saying B over B plus C, right? So it'd say, all right, the total of this group is this. But the issue is that I'm directly setting force of Bn. This could mean it either goes up or it goes down. But I know that what I mean to do is for everything to go down. Okay. All right, maybe I'm seeing it. Maybe it's like minus some proportionate share of the difference between the group total and the new group total. So it'd be like 2/3 so it's like this. So we force of B plus force of C minus is equal to some. I'll say df, whatever, right? So I guess in this case, I know that df would be equal to this value. So I say, all right, you are going to get you are going to get I guess the thing is, like, if they were the same force, then it would work, right? But they would also share just half of it, right? So it's not a perfect solution, but I think somewhere in there is sort of the perfect solution. I mean, I'm like, okay. I'm looking at this graph. I see, obviously, there is only one option. This is the share of forces that are equal to them being properly distributed. And also, the resulting angle change is the target angle change that it needs to be. There's only one solution. But I also know that given my restriction that I placed, there is one choice. But I also know that this line that kind of runs down the middle still is kind of like a place of stability. It's not exactly maybe equal parts, but this is saying I'm taking less force than I was meant to do, but I'm also applying more angular change than I was meant to, which means they could sort of cancel out. Down here, I'm taking more force than I was meant to share, but I'm applying less angular change than I needed. So it's like the other side applies more, I apply less. Or it's sort of like multiplying these two together. The other side is doing less, and I'm also doing less. So maybe it works. Up here, the other side is doing more, and I'm also doing more. That's the idea, right? So I want this to be minus its portion. So it would be d of f times this equation, right? So I'll take my current force and subtract my share of it, or whatever that is. So this could be 1/3 minus, I'll make this 3 times this plus that. Why did that happen? Oh, so we're minus, I meant to write plus. Plus. 2895 something. So it would be 2895 is just slightly off of that. But then I guess I write the other one. 2438. I'll put these points in here. It is on the white line, right? I mean, that should be expected, I guess. Make that point way larger still. So it is actually really close to this intersection, but it's on the white line, which means it's taking the same amount of force but doing less rotation than it was supposed to, which is sort of bad. So that's proportioning the share like that. But then I don't know, maybe what I do is I have this point and I say, all right, now cast this point up to the closest point on this pink line. Maybe I say, all right, I've got this one. The closest point is probably like here, right? So maybe somehow I can do all the math to get that to happen. What is this? Oh, I'm just deleting that. Just delete that. Yeah. I guess I can just say this equals that. And these are my new forces. And like I said, I guess I have this line, right? Where this is the share this is a share of overall force that reaches the angle. But then since it's taking more force than it was meant to, it's maybe not ideal. This can be it for tonight. I'll be back tomorrow. Still, like I said, still thinking about this. I think this might not be the right way to go because in my test, I have a step where I am just totally ignoring that a perfect solution exists. The share of the forces matches what it was supposed to be given, and the resulting angular output matches its target output. This is kind of this extra bit is something that I'm imposing on it, which is probably, I don't know, not what I should do. But I guess the idea here is what if these two lines just don't intersect, right? So maybe this is the backup. I do this. Well, I guess in this case, the most stable solution is to be up here on the white line as close to the blue line as possible. which is to just do 0 force on one of them, on B in this case, and do apply max force on C. But I guess the part that I'm also skipping here is that changing these angles also means this value would change. So because I decrease both of these, maybe this value decreases as a result, or... Wait, I don't know what I did. Let me just pretend that this one decreased. This angle would also decrease, which does that, right? So this goes up, this goes down, right? But I mean, I guess there is still a point where it's like, yeah, this side has really high angle, but the other side, it needs to reach like, the other side has a really small amount or something like that, right? Like, how would you balance that? I guess this would go back again and say, all right, well, maybe this is a really bad group. Maybe there's a better group that does a better job of balancing. I don't know. Which would affect whatever I calculated the white line to be. Like, it's a very complex system, right? So, yeah, that's it for today. I think you just start with that. I think you just say, all right, if they intersect, pick the point, and then if they don't, maybe I find examples where that doesn't happen and then see if this idea leads to something that is as stable as possible, because that is still also a thing. There's definitely a way to minimize the angular rotation that happens anyway. But I guess the issue is that the ways that I'm coming up with now, I think definitely favor dropping some point to 0 and then shooting 2 other points like to a value higher than 1. I mean, that's what I found with the other case, and it looks like it would still happen here. Because if this has an intersection outside, right, now the intersection says, all right, give this one 0.74 and give B 0.74 and then C negative value, which just, that's not physical. That doesn't make any sense. Right. Okay. Thanks for watching. I'll be back tomorrow. Goodbye.